Now, I think I'll start out with a little bit of a sobering topic, which is a lot of AI projects were predicted to fail by Gartner by the end of this year. How many folks have been on a failing AI project? Any brave souls? Okay. Give that man a round of applause for his bravery. And I think that when you look at the challenge with projects, the key contributing factor identified in the study was lack of alignment with business value for the organization, which it's, I think when we started out with AI, it was a new tool. It can do our kids' homework. It can write poems. It can do pretty much anything if you ask executives and C-level folks in most companies. But actually solving concrete business problems, giving accurate, reliable answers, and being able to explain the results is quite challenging. So to start out with, I have a short example of why this is challenging. So we're going to do a word problem. And this is both a test for all of you. So you'll answer this problem, and also for the LLMs. So I have the response from the latest GPT-5 models, so you can kind of compare how they think and where some of the challenges are. And I set up a problem which is designed to bring out a little bit of biases. So I think where you get AI to have the most interesting responses is you kind of mix some bias issues, some reasoning challenges, and also give it something which requires logic that it has to work through. And when you combine all these together, you can trip it up a bit. Also, well, let me read the first problem, and then I'll continue talking. OK, so the first half of this for you all to think about is a school has an elective course choice of computer science, sports, or home economics. This computer science class has 36 students seated in a grid of desks. All the desks are occupied, none of the girls is sitting next to another girl. Also, none of the girls is sitting diagonally from another girl, but there's a maximum number of girls. We want to find out the maximum number of girls this class layout allows. And we'll do this in two parts. This is part one of the question. And if you notice, I put in a little bit of bias here, right? So we know that computer science is, unfortunately, has a lot more men than women, so there's a bit of a gender diversity. Also, like economic disparity in terms of disadvantaged kids getting access to computers. I am also co-running the CNCF Kids Day together with Cassandra, who's sitting in the front. She's also one of our Lightning Talk speakers for tomorrow. And what we try to do with that program for KubeCon events is to have more opportunity to bring young people, bring folks who normally wouldn't have access to computer technology, and then give them examples of cloud-native technology, of programming, and help to get them an advantage where they can actually enjoy and like doing some of the stuff. OK, so any brave souls who want to kind of talk through how they would solve this problem? So how would you look at solving this problem? And just raise your hand if you want to quickly give kind of a summary of how you would think about this, and I'll repeat it for the audience since it'll be hard for them to hear you. So any brave souls? OK, we got at least one brave soul. But basically, like, how would you go about solving this problem as a human? OK, so gentlemen, right there, please go ahead. OK, so like you'd start out and you'd kind of diagram the class. And he said a pen and paper and start drawing it. What would you draw when you're trying to figure this out? OK, so you create a grid of desks and you start spacing out the girls. What size or shape would the grid of desks be? A grid of what? Circles. OK, so I think that's really good, right? So we kind of draw like one in the corner and we'd space them out. Now, anyone else have anything to add to this, like thoughts about how to solve this problem or how to think about it? OK, you were just thinking in your head. You have grid? OK, so like we also need to figure out the grid size, right? So like what size is the grid? And it could be 6 by 6.
7 by 5.
7 by 5, well, that's 35. That doesn't count. But 8 by 4 as well. OK, and then like I think if we wanted to do the grid layout, and kind of like you were saying, draw it on a paper, we'd end up with maybe a few different shapes of class grids. I excluded 1 by 36 because it felt like a row, and that would be hard to fit in a classroom of any size. But like, you know, we'd come up with this, and then we'd start drawing in where the girls could fit, right? So kind of spacing them out and making sure they'd fit, and then try to find the maximum here. So hopefully I did this right, but what do you all think is the maximum given what we've talked about? Any human consensus here? What about the 12? Is that good? OK. See some people nodding. So we'll go with human consensus on 12. Now, let's see what the model did for the same exercise. And basically, I did the reasoning mode, so it kind of talked through it and captured some of the output. It's a little small to read, but the important thing to highlight here is it referenced this classic problem. There's a bunch of research papers on it called the non-attacking kings problem. What LLMs are really good at is they take in a lot of data sources. They do essentially like vector embeddings of them to identify similarities. And this was the most similar logic problem that related to this because, you know, kings attack in that pattern. And how many kings could you fit on the board without them attacking each other? Because it's a chessboard, it's of course square. So it excluded the idea that we'd have different grid shapes. And it gave a maximum of 9 girls. So humans already well ahead of the LLM. Give yourselves all a round of applause. Now let's take the second half of this problem. So teacher's a harsh grader. 75% of students fail out. That's an awful teacher. Not going to raise a lot of great computer scientists. How many new students joined the home economics course? OK, so we had a computer science class. If 75% of the students fail out and leave, they either end up in home economics or sports. So how would you go about thinking about this? How would you figure out which kids leave and they join home economics and which ones join sports? Any ideas about solving this? OK, so like this is a non-deterministic problem, right? I basically set up a problem that can't be answered because we don't have enough information. So maybe half the kids go to home economics and half go to sports, or maybe you look at statistical information on the percentage of kids who prefer that based on gender or something. But we don't have enough information. But ChatGPT always has an answer that's authoritative, that will convince you it's the right answer and possibly is wrong. And what it came up for this after 40 seconds of noodling on it was that, of course, all failed girls, and based on its previous number, there were now 7 failed girls based on the previous answer it gave, join the home economics course. So all girls do home economics, all boys do sports. Another bias, which if you ask ChatGPT directly about this, it would say, well, of course, you know, like kids enjoy different activities. There's a range of things they might do. There might be some biases, but of course, you're going to get a mix of kids. But when you mix in a logic problem, now we've pulled out a fallacy. And what's happening here is the LLM's really only thinking with half of a brain. So it's really, really good at imagination, holistic thinking, intuition, arts, rhythm, nonverbal clues, like all of these like extrapolation type things, where if you ask it to generate an image, you ask it to do these things, it can extrapolate off a large database of stuff. It's not particularly good at logic, sequencing, linear thinking, math. Of course, it can do more complex math now that they mix in various additional models to support those cases. It only knows the facts it's trained in, so if you ask it about things in an enterprise business use case or confidential information, it won't have access to that. And it doesn't think in words, it thinks in word vectors, and it results in a lot of hallucinations, right? So this is one of the big challenges with building very comprehensive applications off of LLMs, is you can't reliably get back answers from it because there's a lot of hallucinations in the data set. I give a very simple example of something we can all think about, right? Like schools and class sizes and grids. Imagine if instead you gave it an enterprise case about supply chain and airline components, and then like trying to solve a very hard like repair job. If there was some document buried somewhere in the knowledge base, kind of like the attacking kings problem, which led it to an incorrect answer, you would have no idea. Out of the tens of thousands or hundreds of thousands of documents fed into it, where it's extrapolating and pulling an incorrect repair diagnosis, and that could be a very, very costly mistake for a technician to make on a real project. Okay, so one of the ways which we can solve this is by using GraphRAG. I'm going to talk a bit about how you can do this with graph databases using Neo4j, which is an open source graph database. We've also integrated into the open platform for enterprise AI, the OPIA open source project, which is part of the LFAI. So I think that you'll hear a bit more about different LFAI projects, but this is one of them which is exciting, and there's a lot of great work going on. And when you pull in techniques like GraphRAG, you're able to get better answers than you would from purely asking an LLM or doing baseline RAG with vector databases. GraphRAG gives you a more grounded answer. So if we ask the LLM directly on a healthcare case, in this case we're asking for the care plan associated with Andrea Jenkins' emphysema. If we ask the LLM directly, it knows what emphysema is. It knows like general information about the condition, and it can give us a very generic answer about preventing further damage to the lungs, involve advising the patient to yada, yada, yada. So it doesn't know the patient's information. It doesn't know anything about her particular issues, but it can tell you in general about emphysema, and it will gladly give you a definitive diagnosis with very little information. Now, we can help that out by adding a vector database. That's kind of the center. So we can ground the information with a vector database, give it a bunch of documents and information about different patient records, and now it can give a better answer. So it says, recommends activities like respiratory therapy, deep breathing, coughing exercises. Presumably these are pulled out from the patient's record. And it's a better answer, but it's incomplete and not a full diagnostic. If we mix in GraphRAG and we give it a knowledge graph, which has both the diagnosis and also information about different health conditions, then we get the best answer. And in this case, it's recommending medication management, smoking cessation counseling, pulmonary rehabilitation exercises. So this is closer to what a doctor would need to prescribe or would need to talk through a patient to help them improve and to address their situation. Typically, where GraphRAG excels is where you have multi-hop queries. So if you could answer a question with a single similarity search, the center one, the baseline RAG, is usually sufficient. So if I can answer the question by simply asking about the patient's information and like their previous care plan, it will give a reasonable answer. When you start mixing in what is the patient's plan, what is guidance for emphysema, like look up relevant medical records, and you're pulling in multiple different sources, that's where it gets quite challenging, and LLMs have a lot more trouble answering those sort of complex questions. Okay, here's an architectural pattern for how you can build an application like this using GraphRAG. Basically, when the user asks a question to your Gen AI application, now rather than going directly to the LM, you ask a graph database information and do a retrieval lookup, which now has access to both similarity information, so vector embeddings, which will give you initial results which are close. And then you do a second hop where you look up relevant graphs which are linked to those vector results. And so this gives you back subgraphs which you can now traverse and you can pass into the LM. And you can also apply some graph data science algorithms, like if you do community grouping algorithms or k-nearest neighbors, you can organize the graph in a way where you get more relevant information to the LM quickly. And then the subgraphs get passed into the LM, and you get an answer which is more explicit, has more context, and gives you something closer to what I showed you in the previous one. Now, that pattern would be the bottom left one, vector search with graph context, where you do a vector search first, and then you look up related graph context. You can also do text to cipher. The LLMs are getting increasingly good at generating cipher, which is the query language for graph databases, directly. So you can directly generate cipher queries, ask the graph, and I'll show a demo of that. You can do vector search with graph context, which is reasonable and easy to do and always gives a good result. I'm going to show a demo of that. So that's the two demos I'll show today. You can also do great stuff with agent and multi-step queries. And then graph filtering is another pattern where if you want to reorder the results to get things higher in the context, you can use the graph as well to do that. So there's a lot of different ways to apply GraphRAG. In general, anything which involves graph lookups and retrieval for doing graph patterns is considered GraphRAG. And there's a lot of great research on different patterns for doing it with graph databases, with graph neural networks, and getting better results than you could just off of a vector encoding. Some reasons why this is helpful, for example, in the health diagnostic case. Now, we not only can give in a subportion of the graph, but we can start doing role-based access by saying the customer service agent has access to the phone number, but the doctor doesn't have access to the phone number. They shouldn't have patient confidential information. The doctor does have the health diagnosis because that's their purview, whereas the customer service wouldn't have access to that. They just have the personal information about the customer's phone number, address, et cetera. And you could do this by annotating the graph with tags or putting roles on the graph. And it's another way where you can take advantage of a structured approach to organizing the data which is available to the LMs. And then I talked a bit about explainability. You also now can explain why you're getting back certain results by looking at the graph and seeing what portion of the graph was passed into the LLM to answer the query, and then adjusting the relationships or improving the quality of the graph to get better results over time. So this is another way which you can improve what you're doing. So let's look at a demo of this technology. And what I'm going to do is use a tool called the Knowledge Graph Builder. So this is an open source tool which basically showcases a bunch of these patterns. It's a web user interface, so you can just go to the LLM Builder website and try this out yourself. It allows you to import a bunch of data sources. So I have 2 different data sources I set up here. One is a VEX document, and the other one is an SBOM. And you can see here the SBOM is just a software bill of materials for a project, so it shows all the different dependencies with SHA checksums. The VEX document relates to this, but it overlays security information. So these are pretty typical artifacts you'd have in a software project. You can do this with any sort of data. You can do it with healthcare data. One of our customers is doing this with a legal use case where they loaded up hundreds of thousands of legal documents and do case lookups on it. But I think this is kind of an easy one to understand and get started with. So you load up your documents. I've already loaded these 2 up. This is set up on a free Aura instance. So again, you can set up a free account yourself or use a local graph database if you want to. And I've hooked it up with the credentials already. And then I had it generate a graph, which didn't take too long. And we can take a look at the structure of the graph and see what it looks like. So here you can see that the generated graph has a bunch of information in it. And we can kind of zoom in and navigate it. This is a part of the VEX documents. And then attached to it, let's look at some of these random nodes. OK, so here's the information from the National Vulnerability Database, which is one of the big databases of vulnerabilities. It has information here on the different artifacts and diagnostic. And it's all kind of linked up in a way where the LLM can look at it. And then what we can do is we can also, in the user interface here, we have a little LLM hooked up to it, and we can ask it questions. So if I ask it a question about a random software component it knows nothing about, and a little typo to show you this is real. Let's pick the Jasper library. So there's nothing mentioned about this in the document, and we'll see what it comes up with. OK, so it doesn't know anything. And that's great because if it doesn't know the answer, we want it grounded where it won't give us an incorrect answer and it won't try to hallucinate and answer about stuff it doesn't know about. The vulnerability in the library, which actually is there, is this Jackson vulnerability, which is CV 2020-25649. It knows which version of the library it is. It knows a bit about the fixed status of it. And it knows about different databases it's referred to. So, pretty good. It pulled out some relevant information from the documents. In part 2 of the demo, we'll see if we can improve on that a bit by using additional technologies. OK, there's my backup.
Ready to
All right. And then, sorry, we'll get to the fun videos in a sec. So, and we're going to do this by having agents and AI talking to AI to improve things. So I think that another way which we're all building applications is by using agents where you now have multiple AI with the same or different models, kind of getting answers, checking each other, doing workflows with recursive patterns. And the best analogy I could come up with for agents was some references to cartoon shows back from the early 80s, which I think pretty much describe the pattern for how agents work. OK, so this is one of the cartoons which was brought to the US from Japan in the early 80s, so I'm kind of dating myself a bit. But it was known in Japan by this name, which I can't read. So for the folks in the audience who are Japanese, you'll be able to read this. And it basically is, you have these 5 robot dragons, I guess, or dogs. And then they fight the bad guy. Of course, individually, they get beat up because they're wimpy. But then at the end of the show, they transform into a giant robot and work together. And of course, they're more powerful, and then they vanquish the bad guy. And this kind of repeats every episode where they have a new bad guy they beat up. So I think this is a great explanation of how agents work, because individually, AI kind of sucks. Right? Like for coding agents, for any real work, having a single AI try to do work, it hallucinates. It gives you bad results. It doesn't actually think deeply enough to answer the question. And then if you give a second LLM to check the work, or if you have like one LLM which is doing planning, and then a bunch of LLMs which do different parts of the problem, then you get typically much better results than you can with a single LLM. Kind of like our friendly robots which work together. And when you think about agents, there's different roles which they take in the system. So we want to use them to automate complex enterprise workflows, do some reasoning and planning to solve the problem, and then take advantage of different tools. And then some of the agents might be involved doing like observations, so they're responding from different actions in the system. They're kind of doing that thought process to reason about what the next step should be in the workflow, and then taking actions with different tools that are available to them. And so now, by taking advantage of agents, we can build systems which are more complex and do planning and reason and executing tasks for systems. So here's a simple architecture for how you could construct an agent system. So in this case, the agent runtime has an orchestration or agent brain, which is doing the profiling, getting the instructions. It has some memory associated with it for short-term memory for storing the current task it's working on, and then long-term memory about previous conversations and previous responses that it's given. We're doing some model-based reasoning and planning to try to figure out what the activities should do. And then these are calling out to LLM agents. So we have one or more models which they're using for executing the tasks, as well as we're embedding some tools in the system. So we have direct connections to APIs, databases, and other things. So this is great, right? Now we have kind of an agentic system that's in this kind of monolithic system. But we can do better with this. And the biggest challenge with this is we've now tightly coupled our tools, which are doing tool calls, to the runtime that's doing it. And this makes it much harder to evolve the set of systems we're accessing to address issues with different versions of tools or external systems we're accessing. And it also means that we're maintaining our own tool systems, right? We don't have an easy way to decompose them and use them. So I think the way we can improve this is by making the tools a standard, right? So we take these complex many-to-many integrations, and we make this something where we're pulling this out, we're making them reusable, and then we're able to plug in the highest quality agents to do the work with a set of tools. And I think we're all familiar with this now. How many folks are using MCP servers for this problem in the audience? OK, quite a number of folks. And this is an open standard that was created by Anthropic actually just about a year ago, was when it was announced in November 2024. We're in 2025 now. And a simple way of thinking about this is it's kind of like a USB-C port for applications. It standardizes how to connect tools with your AI application. But this also was predicted by our super robot friends. For our video crew, the volume on the relative clips is not constant. So you might want to make sure it's not too loud for the audience.
Form blazing swords!
OK, so you can see that our super robot friends, they also have their tools. So they get giant swords or like, round things they can throw at enemies, kind of like MCP servers. And that's how they kind of further extend their capabilities by having these tools which give them capabilities. And now with MCP tools, we can have a composable and modular architecture with different components. It's easy to share and discover these, so we can discover tools for different databases or different document stores which we're using. It's easy to secure these because now we can upgrade them, we can apply security patches, we can share these as an open source component and project, and it's a low barrier to adoption. And an example of an architecture for MCP servers is you have the MCP client. This is invoking the tools, querying the resources, and interpreting the prompts. The MCP server is the one which actually does this. The MCP server could be a remote MCP server, or it could be a local MCP server. And this exposes the tools, the resources, and the prompts for your application. And then some examples of this would be, you might have a tool which does retrieval and search. It's going to look through a bunch of different files, and this would be able to answer a document Q&A use case. Or another one would be sending a message based on some database record resources. And then this could be based on a prompt for a transcription summary, or updating records. And then the API response could be formatted as a JSON file for the output. So there's a bunch of different ways you can use MCP tools, expose different resources. There's a bunch of open source MCP tools which we've developed at Neo4j for using with graph databases. One of them is a Cypher MCP tool, and I'll show a quick example of this for how you can do Cypher lookups using MCP. A second one is a memory tool where you can start using graph databases as the memory for your agentic architectures. We also have one just for provisioning and setting up new databases in our cloud service. And finally, a data modeling one, which you can use to do complex knowledge graph creation and start to do some more data modeling scenarios. And graphs are also used in things like LangGraph. So a lot of folks are using frameworks like LangGraph and other stuff to build agent frameworks. At the end of the day, you're essentially building a graph with your workflow of how agents communicate with each other. This shows an example of a user going through a router, and then the router decides if it's going to talk to the researcher, the chart generator, or make tool calls. Also, agents are used for graphs, or graph memory. Some examples of startups which are using graphs as the underlying store for agentic memory are Zep, Mem0, and Cogni. Back at AI Ancient Worlds Fair, we did a panel presentation with all the different memory companies doing stuff with graphs. And it was exciting to hear about how they're solving problems like overlaying temporal information for when conversations happen as part of the graph, and how they're optimizing the performance and the lookup so that they can have the agents get the responses quicker for that quicker turnaround time that you need to have agents work. And this one is an architecture example from NVIDIA. Now, this is their whole pipeline for video search and summarization, which is published on their open source project. But you can see the data processing pipeline at the bottom feeds into a vector RAG and also a GraphRAG implementation. So they actually use both of these inside of their agent. And then they also have short-term memory attached to their context management and a whole bunch of the things which we've talked about. So you can see that the folks who are kind of at the cutting edge of this are doing some great work with graphs, with agent memory, with GraphRAG lookups, because this allows you to have a better, more explainable and accurate result from your models. OK, so I'm going to show a second demo. And for this second demo, we're going to use the MCP text decipher tool, which we just talked about. And we're going to do it via Claude Code. So I set up Claude Desktop earlier. And what I set up inside of here is inside of settings, you can see I've added an extra tool, the Neo4j Cipher MCP server. I just did a local install with the tool as a MCPB bundle, an MCP bundle. Configured it with the database credentials, and now it's available as a tool to Cipher when we do a new chat. And we can ask it, what do you know about, what was the library? Jackson? The Jackson library and vulnerabilities from your graph database. So I'm asking it basically the same question. I mentioned a graph database because I want to make sure it uses the MCP tool. So that's one of the keywords in the MCP tool. And it gives a very different, it goes about how it looks up the answer very differently from the previous one where it was a vector plus GraphRAG. So rather than just doing a vector lookup, getting a quick response, and then pulling the associated graph nodes, what it's doing is it's making tool calls out to get the schema of the database. So it's connected to the same database server we were using previously. It's pulling back information about the structure, and then it's creating a plan for how it can get the most important information out of the database. And then it's going to execute a bunch of Cipher queries to actually pull that information out. So it'll pull out information about the Jackson library. It will pull out information about like related information from vulnerability databases. And then it combines this with some of the information it has from its general context to fill in the gaps and give a more complete answer. And it's taking quite a while for some reason due to network issues. So we're going to let this run in the background, and then we'll come back to it in a sec. OK, so basically I've set up the MCP server here. It pulls back an answer, you can see, basically pulling back the schema, getting vulnerabilities from the Jackson library, reading Neo4j Cipher. So it executes a bunch of follow-on queries from it. This is the response I got back earlier for what it pulled back. So Jackson vulnerability found an XML injection attack, and it has details about that. XML processing attack, it has specific remediation steps which it recommends. And you can see, OK, let's go back for a sec. You can see that it's a much longer and more authoritative response back from using the tool like this. So this is where the MCP servers shine when you want a research task or you want something which gives back more detailed information. You can actually use it as a tool against different data sources, and it can give back quite good information. OK, so let's see how we're doing. That is totally going nowhere. OK, we'll forget about that. And I have one last video clip for the audience to talk about kind of how the end of every Super Robot show goes. I think we're getting close to the end of the presentation, and we need to kill a bad guy.
Zaporobi!
OK, so like every good Super Robot show, the translations, by the way, were horrendous for early Japanese movies brought over. So I've shown how to use graph databases, agents, MCP servers to improve all of this. If you want more detailed technical information on how this stuff actually works, my team puts together a free training course called Graph Academy. So it has courses specifically on how to build chatbot agents with JavaScript, with TypeScript, informations on Cypher. We have some new courses coming out on MCP servers and agents as well. So pretty much we try to stay up with the latest Gen AI advances and give that in relation to graph information. A second resource, which is something which I'm working on together with Michael Hunger and Jesus Barraza, is the GraphRAG, the Definitive Guide. So this is a new book coming out from O'Reilly. We've published a preview version of the first few chapters, which is available on Safari and other places where you can get O'Reilly books. And the final book should be coming out about next September. So we're working on the rest of the chapter. We want it to be a very authoritative and complete guide on everything you can do with GraphRAG. So thank you very much for coming to my presentation. I hope you enjoy the rest of the AI Dev Conference and the rest of the sessions today. And I'm happy to take additional questions. Just come up to the stage, and I'll take them after the talk. Thank you so much.